integration is the opposite of differentiation, and the notation that we used for differentiation is we would say the dx was the differential operator and it acts on a function f of x. Now for the integral operator, the way that we write it is we've got this special s which has got this kind of curly bits on the end of it. We integrate a function f of x and then we put dx on the end like this. Sometimes you may also see this, especially if you study physics in later years at university. You may see somebody just put the integral and then dx and then list the function afterwards. Now we tend not to do this because it's hard to know if there was other terms on the end where what you're integrating ends and where the other terms begin. So we tend to just use this bit here, which means you integrate everything between this integration symbol and the dx.
Okay, so now you understand the notation. Let's have a look at an example, and we'll take what is the integral of 3x squared. Okay, so can we do the integral of 3x squared dx? And what we're looking at here when we're doing the integral from 3x squared is, let's think about what would happen if we took the differential of another function. So if we have a look at x cubed, so if we look at dx cubed dx, then we know from our rule is that we've got the derivative of any polynomial, if we remember our rules from the other day, of ax to the n dx is equal to n ax to the n minus 1. Now if we have a look at the derivative of x cubed, then we're going to get the derivative of x cubed is equal to n, which is 3, becomes out the front, x is still x, and the cube becomes n minus 1, which is 3 minus 1, which equals 2. So we'll notice that what we've got here is that 3x squared and that 3x squared match to each other. So if we have a look at this in return, then that means that the integral of this is equal to x cubed. So that is one way we can show an example of how it goes in the reverse. Now, if for example you wanted to do an integral of something that didn't have the right pronumeral in front of it, then what we're looking for is to take that factor out and see how it goes from there. So let's do something a little bit more difficult. Okay, the integral of x squared dx. Now if we know the integral of 3x squared dx, then this is the same as saying the integral of, we've got 1/3 of the integral of 3x squared dx, which from our previous one we know is equal to 1/3 of x cubed. One of the things you need to remember is that when we're taking our derivative, dx cubed dx, then we get equals 3x squared. What if we take the derivative of x cubed plus 3? If we have a look at this, then the x cubed becomes 3x squared, and what happens to 3 becomes 0. That means we get 3x squared again. And this will happen for any value of any constant we put in the end there. And what this means is that when we're taking our derivative, we're finding the slope of the line. We can have any number of lines that have the same slope, and they will all have the same derivative because they have the same slope. So what this means is we have to take that into account when we're integrating. And we have a look at our integral of 3x squared dx. We know that equals x cubed, but it also has some arbitrary constant which we'll call c. What this means is that we need some more information to find out what that value of c is. So when we're talking in terms of mechanics, this might be, you might have an initial velocity, or you might have initial displacement. And when you have those initial velocities and displacements, that sets our bounds.